Hello, welcome back. This time we're going to be talking about ocean temperature and depth. So in the last slides, what we ended up talking about was ocean surface water temperature. Now that's one thing, but what we really need is not the surface water temperature, and we'll talk about that this time. What we need instead is basically when we're looking at the ocean temperatures, we need to go down in order to get a nice steady temperature. Now the reason why we need to go down is because the temperature at the surface ends up changing. That's what NOAA is tracking. That's what they're looking for. They're looking at these weather patterns as well. What we want is nice, steady temperature. So instead of being at the surface, we need to go down, especially if we want the temperatures that we want at a nice, steady state. So the average ocean surface temperature is about 17 degrees Celsius, which is about 62.6. But again, that's surface temperature, not what we want, not at all what we're looking for. Average salinity, 3.5%, fine, which means it drives down the freezing point down to 28.5 degrees as opposed to 32 degrees, which we're used to, or 0 Celsius. So if we drop down to a depth of 1,000 meters, you can see that that drops to the base of that thermocline right there. Now, that's good, but this thermocline really doesn't shift in this last bit. What ends up shifting is this temperature here. It'll slide to the left or to the right. Now, this particular graph was taken from a tropical region, and this will shift to the left depending on the time of year, just the amount of flows, etc., and what's going on. But once you start to get down here, it'll hit this thermocline and be nice and steady. So even if you're shifting, say 3, 4, 5 degrees throughout a year, it's going to hit this temperature and stay there, or hit that level, that thermocline, and stay there. Now this isn't something that's entirely new. So this is something that's been studied in many locations for many years. So once you get a thermocline together, you can pretty much get a predictable temperature that you're going to use. So what we looked at is we started with 1,000 meters at the base of that thermocline, and out of that, we're getting approximately 5.6 here Celsius, which is about 42 degrees Fahrenheit at 1,000 meters. All right, but 1,000 meters going down, that's, basically you multiply it by 9, you have 9,000 feet is what you're going down, 9 to 10,000 feet. Not so good as far as going down. You want to lessen that if you possibly can. So let's see what we can do about that, because we really don't need that 5.6. We need, or that 42. We can go a little bit higher as far as temperature. So let's try around 500. We hit around 500 meters, and that's about 1640 feet. And the idea is that that's about 60 degrees Fahrenheit, 15 degrees Celsius, and depth would suffice for us, but the temperature, that's not going to suffice. So it's a little too high on temperature. So nice stable temperature somewhere right in between. It's what we're looking for. So you can see that this is going to give us about our 45-degree temperature right there. That's 7 degrees or so Celsius, and that's at about 750 meters. So again, that's around 2460 feet as opposed to the 1,000 to, oh, I'm sorry, that wasn't 9,000. It's around 3,000 feet for 1,000. I even put it over here, 3280 feet. All right, so that's basically the ocean thermocline and what we can expect. So let's see what we need to do in order to do that. Well, with the ocean depth and us, what we're looking for, the continental shelf, as shown in this diagram, goes around 200 meters, and we're looking to go to 750. Well, you're going to have to put a pipe down here along the continental shelf and then down the continental slope until you hit your 750. Now that continental slope keeps going, and if you've seen how this looks in other diagrams, you can see that it's kind of a steeper drop off in most locations, but it goes down to 4,000 to 5,000 meters before you hit the ocean basin floor. And along that continental slope, there's a lot of action. So it's not like this is solid, or even the continental shelf is entirely solid. It's a little bit moving. If you want to think of it like the wind's blowing on the surface, It's kind of the same thing, except water has a little bit more weight to it, and whenever things shift, it can cause havoc for a pipe that's not mounted properly. So here we are with the shelf, and what we need to anticipate is, okay, we've got these submarine canyons. We don't want to cross them, so we need to find a nice spot that's maybe next to it or far enough away from it, and down that slope so that we can get a nice gradual mounting that we're not too worried about any problems with changes in the pipe. And the materials that we're using, such as PVC that we're talking about for this, are nice and flexible. They're going to shift based on these things that shift here as far as the surface, and then the mountings that can be done are going to be substantial, so that you won't have to worry about the piping shifting laterally or floating out or anything like that. And not only that, once it's mounted into the side, into the shelf and into the slope, that continental slope, all of this, what's called continental turbidity, or what this turbidity current here, and such. Once it's mounted properly, it's not going to cause a problem for us. So you can see we've got this turbidity that flows not just down the slope, but it also goes across the slope as well. So it follows all axes. And once you mount it to the slope, though, usually you're not having any problems. All right, so that's some of the issues that we're talking about when we're talking about ocean water. But the continental slope also shifts. So in some cases, you're talking about underground tunneling to avoid other things like that. And also along the shelf, you can do that to avoid wave action. You can see that there's wave action on the continental shelf, about half that continental shelf in here. It's going to have wave action. So if you think about a tsunami or something like that coming through, the rest of the pipe is going to be perfectly fine, perfectly protected, even earthquakes for that matter. But a tsunami rolling through is going to be passing along, and it might cause some shifting or might cause stresses that you don't really want, of course, right where the water meets the land. So if you're just thinking of like just having a breaker or something like that, you may want to consider tunneling and getting down to that shelf that way. And it's not really even the weather that's going to have the most impact on piping like that. It's going to be man-made. It's going to be a boat or an anchor or something else. Somebody drops, something heavy or something like that, and they do it in the wrong place, and you have a cracked pipe. Not good. It can be replaced really quickly, really easily, but in the meantime, you're shutting your system down and you're taking out a couple days maybe by the time you're doing all of that replacement. Okay, so those are some of the challenges when working with the ocean. Whenever you're working with lakes or rivers, lakes pretty much have the same thing. You need to anticipate, you need to plan in the same way, but you don't have to worry about the salinity or some of the corrosive issues that the salinity might have in the open ocean, as well as the critters become less, so you don't have to worry about the different types that might be a problem for you. And rivers, of course, have even less issues just because you're not going as far down. But because you're not going as far down, you're more worried about the flow of the river itself as well. Okay. So now that we've talked about that, we will launch into projects very soon.